fast approaching the end of our little exploration of the construction of the real numbers. We just have 3 videos left to do. We're now working on proving that our map phi r is an isomorphism, and we're in the middle of proving this. Last time we proved that it's a bijection. Now we're continuing with, we need to prove that it preserves addition. Then next time we'll prove that it preserves multiplication. And then we'll be done proving this as an isomorphism, and the only thing remaining will be to prove that, in fact, there's only one possible isomorphism. That'll be the last step. Then we're done, and we're moving on to multivariable calculus. So our definition of R is that we take a value here, and that equals the supremum of the set phi q of everything in dr, sending it to the rational numbers in y. And dr is the set of all q in the rationals in x, such that q is less than r. So this is basically a Dedekind cut, and we're taking the supremum. So we're taking all of the rational elements that are less than r, sending each one of them to its mapped rational number in y, and then we're taking the supremum of that set, and that is what phi r maps r to. So I just want to say where we talk for a second about where we are right now, because the way that all of math works is you build off of what you already know. So you achieve some kind of a result, and then you can use that result to move forward and use that result to figure out more things. So what we have now, so far we've shown that phi q is an isomorphism. So we now know about rational numbers, that rational numbers are mapped from x to y. And we've got to somehow, using what we now know about rational numbers and phi q, use that to build our map of R. To do that, we've built a couple of pieces of information. So the main one, so there's a few things that we're using over and over and that we're going to be using from now on as well. That phi q of R equals phi R of R. This is something we proved 2 videos ago, that if R is rational, then phi q of R is the same as phi R of R. So phi R sends rationals to rationals. And the second thing is that because the Dedekind cut is also building real numbers from rationals, it's the set of all rationals that are less than R. So we can use that fact as well, because what we're really dealing with is rational numbers. So everything is about getting back to rational numbers, do the work there, and then go back. I've said a few times, it's like you go down, over, and back. Down to the rationals, over, do your work, and then go back up to what you want to prove. So the other thing that we're using a lot is if we have R is less than S, then because the rationals are dense in the reals, we can always, that means that there's always going to be some rational Q that's between any 2 numbers. So if one is less than the other, there's going to be something in between them. We know that, so we use that piece of information all the time. And also our understanding of the least upper bound, that if y equals the supremum of dr, and if x is another upper bound, is an upper bound of dr, that means that y has to be less than or equal to x, because the least upper bound is less than or equal to any other upper bound. That's the other thing we use all the time. And then, given if we know that one is less than the other, we can use this fact to find a contradiction, which means then that x is in fact equal to y, and then that will show the result that we want. Okay, so I just wanted to sort of recap. These are the pieces of information, the tools that we're using over and over. So now we've done the bijection. We've shown that it's well-defined, 1-to-1 and onto. Now we're moving on to addition. So what we need to show in order to show that phi r preserves addition, we have to show that phi r of u plus v equals phi r of u plus phi r of v, right? And these are any reals. If you add them in x and then map them to y, that's the same as mapping them to y and then adding them together in y. This is what we have to prove to show that phi r preserves addition. So the problem is this we know is the least upper bound of the set of all rationals less than u plus v. This is the set of all, this is the supremum of the set of all rationals less than u, same here for v. If we could just say that the supremum of phi q of du equals phi q of u, then this would be easy because we know phi q and we'd have no problem. The problem is that u is real, which means this is undefined. So we're not able to do that. So we're going to have to find a way, even though these two numbers are real, to get back to the rationals to prove this result in the rationals and then take it back to the reals. So what we're going to do is we're going to start by looking at what if u is any real and v is a rational number. So we're going to have to do it in two steps. First step is to show that this is true when v is rational, then extend that to show that it's true in any situation. So let's change the page. So the special case first. So let u be any element of x and v be an element of the rationals in x. So we need to show that phi r of u plus v equals phi r of u plus phi r of v, where v is rational. So because v is rational, we already know from P3 tells us that phi q of v equals phi r of v. So we can rewrite this using the definition of phi r and then using phi q of v here. So the definition of phi r here is that the supremum, wait, I'm gonna set up. The supremum of phi q of d of u plus v equals the supremum of phi q of du plus phi q of v. Right? This is just rewriting this. This is the definition of this, and this is the same thing just for u. And then we know that because v is rational, that phi r equals phi q of v. This is what we're going to try to approach. Because notice so we've made a little bit of progress here because now we're only talking about rationals, right? So maybe we've made a tiny bit of progress, but we'll see. But u is still real. So we need to figure out what else do we know about this number and this number in terms of rationals so that we can build it back up. So first, the set of d u plus v is the set of all rationals in Q where r is less than u plus v, right? This is just the definition of a Dedekind cut. It's all rationals less than u plus v. Note that then you can rearrange this so that r minus v is less than u, right? So let's just make another variable here just to make it a little neater. Let q equal r minus v. Okay, so we're just rewriting. Now notice r and v are both rational. That means that r minus v is also rational because rational numbers are closed under addition. So q is an element of the rationals too. And we know as well that q is less than v. And we know furthermore that now that we've defined q, if we move the r back over, we have that r equals q plus v, and that since r is less than u plus v, then q plus v is also less than u plus v, okay? We haven't really done anything yet. We've just labeled some stuff, moved some stuff around, but q is now rational, and q plus v is less than u plus v. Oh wait, I said v there, but this is q is less than u, not v. So the next thing is that, let's just label this 1. I don't know if we'll need this, but then 2 is that the set of phi q of d u plus v is the set of all phi q of r where r is an element of q and r is less than u plus v. So remember, the thing about this set is you're doing the comparison in x, then you're moving it to y. So this is all r less than u plus v in x, and then you take phi q of each one of those to get a set in y. And now we already know that phi q is additive, so that means that we can apply phi q here. So we also have that phi q of r, Oh, I'm sorry. We know that r equals q plus v. So we can apply phi q to both sides of this, and we have that phi q of r equals phi q of u plus, I keep making mistakes. I mean q. Phi q of r equals phi q of q plus phi q of v. These are all rational. And furthermore, we can rearrange them again, and we have that phi q of q equals phi q of r minus phi q of v. Okay. More pieces of information for us to use. Notice that we cannot apply phi q to this inequality because u is not rational. So we can't say that phi q of r is less than phi q of u plus phi q of v because phi q of u is undefined. But we do know things about r and things about v in q and in phi q because they're all rational. Okay. So based on what we just said, we can say then that phi q of d of u plus v is the set of all numbers expressible as sums phi q of q plus phi q of v. So phi q of the Dedekind cut of all rationals less than u plus v is expressible as the set of all numbers that can be written as phi q of q plus phi q of v. This is what we just saw in the last one because phi q r equals phi q q plus phi q v. V is fixed for this exercise. So we already know phi q of v. So this is, in other words, just the set where q is less than u. The reason for this is that this set is the set of all r, all rationals r, less than u plus v, right? And then we move this over and we define q to be r minus v, which means that r can be rewritten as q plus v. So this set is the set of all phi r. In other words, the set of all phi q plus phi v. Okay, we can do that because phi q is rational. R is all rationals less than u plus v. Oh, and I don't think I quite said this. Q is less than u because we have from here that if r is less than u plus v, then r minus v is less than u. Oh, and then that equals q. We did do that before. So that's why q is less than u. So phi q of d of u plus v is the set of all numbers that are expressible as phi q of q plus phi q of v, where q is less than u, because v is fixed. So now we're getting somewhere, because note that this set, the set of phi q of du, is by definition the set of all phi q of q, where q is an element of the rationals and q is less than u, right? That's the definition of this, that you take all the rationals less than u and apply phi q to them. So it's all of the q's less than u. So notice that we've made a connection here because phi q of du plus v is the set of all phi q of q plus phi q of v where q is less than u. But also phi q of du is also the set of all phi q where q is less than u. So we're making progress. So we've established that q is r minus v, so phi q equals phi q of r minus phi q of v. So we can replace the phi q with the phi r minus phi v so that the set of phi q of du is also the set of all phi q of r minus phi q of v. So we can write this set in either way. It's either the set of all phi q or it's the set of all phi r minus all phi v. Okay, so now we know that phi q of r is less than the supremum of phi q d u plus v. Now, this is just the definition of phi q of r, because this is the set of all phi q of r where r is less than u plus v. So this is an upper bound, so all of these have to be less than this. That means we can just subtract something from both sides. So we have phi q of r minus phi q of v is less than this again, supremum right? That's nothing. We just subtracted phi q of v from both sides. Therefore, this now is the definition of phi. This is the definition of phi q. So we can rewrite this as phi q of q is also less than the supremum of du plus v minus phi q of v. Now, we know that q is all rationals less than u. So the set of all phi q with q less than u, that's the definition of the set phi q of du, right? This set is the set of all of these when q is less than u. And this is bigger than everything in this set. That means that this is an upper bound of this, right? So sup phi q du plus v minus phi q v is an upper bound of phi q du, right? Because this is bigger than every element of this. But that only means that it's an upper bound. So we're not there yet. So what we have then, this set has a least upper bound. And since this is an upper bound, we have that the supremum of this has to be less than or equal to, because this is the least upper bound, this is an upper bound. So this has to be less than or equal to this. Supremum of q du plus v minus phi q v. Okay? So we're almost there, but we're not there yet, because all we know so far is that this is an upper bound. It's either greater than or equal to this, but we've got to show that it's not greater than so that they're equal. So how do we do that? We're going to assume the opposite and see where that leads us. So we're going to assume, so let's change the page. So we're going to assume that sup phi q of du is less than sup, phi q u plus v minus phi q v. We're going to assume this is true, and what we need to do is show that it's actually not true. So we're going to reach a contradiction, show that this is not true. That means that they must be equal. So if that's the case, when we have an inequality like this, what do? We always insert a rational number in between. So there exists a t element of the rationals in x such that the supremum of phi q of du is less than phi q of t is less than supremum phi q du plus v minus phi q v, right? So what we did is we're picking a t in x, but what we're actually doing is we're saying that because the rationals are dense in y, there's going to exist some rational number between them. But because phi q is onto, that means that there's going to be an x that will give us that number. Okay, so we're using density to find a number between them, and then we're using the fact that phi q is onto to find the t that maps to that number. So remember, just a minute ago, we established that phi q of q is less than this thing. That was what we just established on the last page. Now, if this is true, this is for all q. And here we just showed that the t that we chose also is less than this. That means that there's some q that equals the phi q of t. So phi q of q equals phi q of t for some q element of q, right? That means that phi q of t is an element of phi q of du, because q is all rationals less than u. T is one of them, so phi q of t now has to be an element of phi q of du. But we started by saying we chose t specifically to be bigger than the supremum of of du. That means that this is not an element of phi q of du. That was our assumption. And we just showed that if that's our assumption, then in fact phi q is an element of this. That means that our assumption must be wrong. So our assumption is wrong, therefore this is not true. The supermem of phi q du is not less than supermem of phi q of du plus v minus phi q of v. Therefore, we've done what we wanted to show. We showed that therefore the supermem of phi q of du plus v must actually equal, because it's not less than, so it has to be equal to the supermem of phi q of du plus v minus phi q v. And this was what we were trying to prove. Oh, I'm sorry, no, this one is just the u. This is u. What we showed is that the supermem of phi q of du equals the supermem of u plus v minus phi q of v. So now, well, can you read that? There. Okay. This is just the definition of phi r of u, right? This is the definition of phi r of u plus v. And this, from P3, phi q of v equals phi r of v, because v is rational. Rearrange them, and we have that phi r of u plus v equals phi r of u plus phi r of v when v is an element of the rationals. Great, that's what we wanted to show. Okay, so we've shown that as long as one of the summands is rational, then phi r preserves addition. We're more than halfway there. Now we just need to go to the general case, using this, show that if it's true when one of them is rational, then it's true all the time. So last thing, general case. Let u and v be elements of x, and let q be an element of the rationals such that q is less than v. Okay, so these are now arbitrary reals. Q is a rational such that q is less than v. So before v was already rational, now v is also a real, but we're still looking, we're just gonna start with rationals that are less than v and see what we can conclude from that. So we'll start with q less than v. That implies, add u to both sides. We have that u plus q is less than u plus v. Now, we already showed back, in order to prove that phi r is 1-to-1, that phi r is order preserving. So if u plus q is less than u plus v, then phi r of u plus q is less than phi r of u plus v. Okay? Now, we just finished showing that if one of the summands is rational, and here q is rational, u is not, but if one of them is rational, then phi r is order preserving. So this means that phi r of u plus phi r of q is less than phi r of u plus v. Okay, now let's move the u to the other side. So we have phi r of q is less than phi r of u plus v minus phi r of u. And now, because this is rational, using P3, we have that phi q of q is less than phi r of u plus v minus phi r of u. Okay, now what? So q is the set of all rationals less than v, right? That means that the set of all phi q's with q less than v is the set phi q of dv. So the set of all phi q of q with q less than v is the set, that is this set. So if phi q of q is less than phi r of u plus b, v minus phi r of u, is true for all q less than v, then this has to be an upper bound of this, right? This with all q less than v is the set phi q of d v. And if this is greater than all of the elements of this, that means that this is an upper bound. So phi r of u plus v minus phi r u is an upper bound of phi q dv. We're very close. Now we do the same thing that we did last time. If this is an upper bound of this, then the least upper bound of this has to be less than or equal to this. So therefore, the least upper bound of phi q dv is less than or equal to phi r of u plus v minus phi r of u. So you should know now what we have to do next. We just have to prove that in fact this is not less than this, therefore it must be equal. To do that, we're going to assume the opposite. So we'll assume that the supremum is less than this and show that that reaches a contradiction. First, note that what is this? This is just the definition of phi r of v. So what we just showed is that this is the definition of phi r of v. So we've shown that phi r of v is less than or equal to phi r of u plus v minus phi r u. We're very close to the final result. We just have to show that it's not less than, and we're done. So let's do that on the next page. So assume that phi r of v is less than phi r of u plus v minus phi r of u. What do we do whenever we have an inequality? We insert a rational number, right? So we're going to do the exact same thing. Then there exists a t element of qx such that phi r of v is less than phi r of t. And remember, we can say this because since t is rational, phi q is going to equal phi r, right? Is less than phi r of u plus v minus phi r of u. Now we've already shown that phi r is order preserving, therefore v is less than t. Okay, so we've shown that v is less than t, so now we're going to use that. So if we have that we're given by assumption that phi r of t is less than phi r of u plus v minus phi r of u. Now, because we just showed that v is less than t, that means that that is less than phi r of u plus t minus phi r of u, right? This is going to be less than this because phi r is order preserving, and if v is less than t, then u plus v is less than u plus t. So then that means that phi r of u plus v is less than phi r of u plus t, so this is less than this. This equals, what do we know now? T is rational, right? That means that we already know that phi r preserves addition, so that equals phi r of u plus phi r of t minus phi r of u, right? Because we just showed that in the special case where t is rational, this equals this. And now we just cancel these and we're left with phi r of t. So what did we just show? We just showed that if we assume this is true, then that means that phi r of t is less than phi r of t. That is impossible. That's technique 5. That if you can show that a is less than a, then you've reached a contradiction because this is impossible. So the assumption must be untrue. Therefore, it must be that in fact phi r of v equals phi r of u plus v minus phi r of u. Therefore, rearrange it, and we have phi r of u plus v equals phi r of u plus phi r of v, q, e, d. We did it. Okay, this means that phi r does preserve addition. That was hard, right? Step by step, it's not hard, but it's just very involved. And that is, I think, about the hardest thing that we're going to have done so far. I don't know when we'll come back to something as hard as this was. We're here now. Now, for multiplication, we're going to have to do something very similar in a little different way, but we basically start the same way. We start with something times a rational and then extend it to the reals. Then we show that the reals are rigid by showing that this is in fact the only isomorphism, and then we're done with this and we're moving on to a new topic entirely. Thank you, and I will see you next week. Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.